I'd like to discuss in more detail today some properties of Bose gases at very low temperatures. Remember our qualitative discussion of Bose gases at low temperatures? At the beginning of our discussion of perfect gases, when we talked qualitatively about Fermi and Bose gases, remember that we said that as the temperature approaches zero, the ground state acquires a macroscopic occupation. We're considering the case where the number of particles, the total number of particles is fixed, and we let the temperature go to zero. And then, of course, mostly the low energy states will be occupied, and since there is no restriction on the number of particles that you can have in any given state, as we have in the case of fermions, eventually the ground state acquires a macroscopic occupation. And I'd like to go back to the discrete case. We have used a lot the continuum limit recently, but for the sake of this discussion, I'd like to return for the moment to the discrete case. So we have discrete levels epsilon I and an expected occupation Ni of these discrete levels. So let's say here are our very narrowly spaced discrete levels. For perfect gas, the ground state energy is equal to zero. And as I said, as the temperature approaches zero, this ground state will acquire a macroscopic occupation. And the levels above may still have also particles in them, but this will decay rapidly, and a significant proportion of all particles is now sitting in the ground state. This is what's going to happen as the temperature goes to zero. The formula for the expected occupation of a given level, read Ni, for simplicity I'm omitting now these expectation value signs. Ni, the expected occupation, is given by 1 over, let me write it in terms of alpha rather than the chemical potential, so e to the minus alpha, e to the power inverse temperature epsilon I minus 1. In particular, the occupation of the ground state, that is the state with energy 0. The occupation of the ground state, let me denote that by a capital N with the index 0. Capital M because we are looking at the scenario where this ground state occupation becomes macroscopic, and therefore it deserves a capital letter. Well, in the ground state, epsilon 0 is 0, and the formula simplifies. This is just 1 over e to the minus alpha minus 1. You can solve that for alpha. This is then minus the log of 1 plus 1 over n naught. As the temperature goes to 0, we said that this ground state occupation becomes macroscopic. So n0 becomes very large. So 1 over n naught becomes very small. And this allows us to expand the logarithm and say this is approximately equal to minus 1 over n naught. Now, as the temperature approaches 0, then eventually all the particles will be in the ground state. So this goes to minus 1 over n without the subscript. the total particle number is huge, of the order 10 to the 23, typical order of magnitude. So minus 1 over n is practically 0. Yeah? So this is, for all practical purposes, just below 0. That's why I write the 0 minus. It's just below 0. Now, for this consideration, on purpose, I used the discrete language because the continuum limit has a problem here. The continuum limit fails in this scenario. Because in the continuum limit, remember that we obtained a formula for the partial derivative with respect to alpha of the grand canonical partition function, a general formula for that, in the continuum limit. Under normal circumstances, this is by definition, or by our general framework, equal to the total particle number. And we had discussed that the total particle number can also be written as, or obtained by integrating from 0 to infinity over all energies, level density times occupation factor. This relationship that I just wrote still holds. Yeah? You can start from the grand canonical partition function, which still has this form that we had derived, integral from 0 to infinity over all energies, and then this curly n of epsilon times the occupation factor. If you define the grand canonical partition function in this way, as we did in the continuum limit, then this equation that I just wrote still holds, only that this is no longer the total particle number. Why is that? That's because the level density, remember for non-relativistic particles, the level density, the d of epsilon, goes like the square root of epsilon. So at epsilon equal to 0, at the ground state, the level density vanishes. And therefore, a possible macroscopic occupation of the ground state is not taken into account, is not included in this integral. Because at epsilon equal to 0, the level density vanishes, and therefore the integral fails to take into account the macroscopic occupation of the ground state. Yeah, so this is the point. This integral that we had derived in the continuum limit fails to include the macroscopic occupation of the ground state. And for this reason, the above expression, integral over level density times occupation factor on the right-hand side, or the partial with respect to alpha of the log of the grand canonical partition function as defined in the continuum limit, namely this integral over n times f, this is no longer the total particle number. Rather, it accounts only for all the other particles outside the ground state. So this derivative with respect to alpha is now no longer n, but it's n minus n naught. It's all particles except the macroscopic occupation of the ground state. Now we learned that as the temperature goes to 0, not only does the chemical potential go to 0, that's what we had discussed already in our qualitative analysis of the Bose gas at low temperatures, but we learned that moreover also the parameter alpha goes to 0. That's not self-evident because alpha is beta times mu. Mu goes to 0 and the temperature goes to 0. So beta times mu, that's mu divided by kT. It's not clear whether this also goes to 0, or whether it remains finite or even diverges. But what we found on the previous page is that the alpha goes to 0 as well. Now, this fact allows us to evaluate the grand canonical partition function. And when I say grand canonical partition function, I always mean the grand canonical partition function as we had found in the continuum limit. So this integral curly n of epsilon times occupation factor, this grand canonical partition function, which describes, as we saw on the previous page, only the n minus n naught particles that are not in the ground state. Now, the fact that alpha goes to 0 allows us to approximate that partition function with a Taylor expansion around alpha equal to 0. So the idea is to Taylor expand the log of the grand canonical partition function as defined in the continuum limit, to expand that around alpha equal to 0. We look at non-relativistic particles in 3 spatial dimensions. In that case, we know that the number of states up to epsilon, which features in this integral, goes like the spatial volume and energy to the power 3/2. Then we can substitute in the integral, it's an integral over the epsilon, we can substitute x for beta times epsilon, as we have done several times before. And then we find the general formula still without Taylor expansion. We find that the log of this partition function is proportional to volume, beta to the power minus 3/2, and then we have an integral from 0 to infinity dx x to the power 3/2 divided by e to the power x minus alpha minus 1. Now, this is a very special integral which cannot be calculated analytically, and this is the only term in the formula for the partition function that carries a dependence on alpha. So when we say we want to Taylor expand the log of the partition function around alpha equal to 0, what this means is that we should Taylor expand this integral, this f of alpha, around alpha equal to 0. So what we do here is that we Taylor expand f of alpha. We say this is, we go up to first order, this is f at alpha equal to 0 plus f prime at 0 times alpha. And you can calculate the f of 0 and the f prime of 0, but this shouldn't concern us here because we want to understand only the nature of the dependencies on the thermodynamic variables. So for our purposes, it will be enough to say that the log of the grand canonical partition function in the continuum limit as a function of beta, alpha, and v depends on these thermodynamic variables in the manner it's proportional to volume. It goes like inverse temperature to the power minus 3/2, and then as for the dependency on alpha, we can write this approximately as 1 plus f prime at 0 over f at 0 times alpha, where the f prime and the f of 0, they are just numbers. We saw on the previous page that the partial derivative of the log of the partition function in the continuum limit, that this no longer gives the total particle number, but only the number of particles outside the ground state, the number of particles up to this macroscopic occupation of the ground state. So we found that this is only n minus n naught. For the log of the partition function, we just found this approximate formula in our first order Taylor expansion. It's proportional to volume beta to the power minus 3/2, and then this bracket, when you take the derivative with respect to alpha, then obviously the first, the one in the bracket gives a 0 when you take the derivative, and only the term proportional to alpha will survive. And hence, this derivative of the log of the partition function with respect to alpha in the low temperature limit goes like the volume times beta to the power minus 3/2 and is no longer dependent on alpha. So this is then independent of alpha. If we Taylor expand, we get an approximate formula for the continuum part of the grand canonical partition function. This gives us an approximate formula for the number of particles outside the ground state. This helps to understand the phenomenon of Bose-Einstein condensation, and in particular it helps us to estimate the temperature, the so-called Bose-Einstein temperature, at which this Bose-Einstein condensation sets in. When we talk about condensation, what we mean is that the occupation of the ground state becomes macroscopic. The formula that we just derived on the previous page gave us the number of uncondensed particles, so particles outside this ground state, as a function of temperature in the low temperature limit. And in the low temperature limit, we found that this number of uncondensed particles grows like temperature to the power 3/2. Now this approximate formula will be valid up to some temperature, and then the quality of the first order Taylor expansion will deteriorate, and this will no longer be a good approximation. So let me say this is a good approximation up to this temperature that I indicated here, and then afterwards for higher temperatures this is then only a rough estimate. Certainly the number of uncondensed particles can never exceed the total particle number. So somewhere here we have the total particle number n, and then at that point, at the latest, our approximate formula from the previous page will break down. In order to get a rough estimate for the sort of the typical temperature scale at which you have Bose-Einstein condensation, to obtain a rough estimate, what you can do is you can look at this point here, where according to our formula, the number of uncondensed particles equals the total number of particles. So that's the temperature at which then the ground state is empty. This should happen at some temperature scale, Bose-Einstein temperature. So we could use this as for a rough estimate of the temperature at which this condensation sets in. So according to this idea, we can say that condensation sets in at the temperature, the Bose-Einstein temperature, where n minus n naught, so the number of uncondensed particles, is equal to the total number of particles. So where we cease to have, if you lower the temperature, then at high temperatures the ground state is virtually empty, and then at a certain temperature scale, at the Bose-Einstein temperature, the ground state begins to acquire a macroscopic occupation, and we said, sort of to have a rough estimate, this is this point where the blue curve reaches n. So n minus n naught is equal to n. Then we can use the formula that we had obtained for the number of uncondensed particles. We said that this went like beta to the power minus 3/2. And we can solve that for beta and in turn convert this into a temperature, and we find that the Bose-Einstein temperature should go like the particle density to the power 2/3. You can do a precise calculation with the correct level density to get all the prefactors right. Such a precise calculation with the level density for 3D non-relativistic particles and possibly some degeneracy G yields the precise formula for the Bose-Einstein temperature. It's given by 2 pi h bar squared divided by Boltzmann constant times mass of the particles in your gas. Then you have the number of particles divided by volume, so the particle density, as before, to the power 2/3. And then in the denominator in front of the V, there's still two prefactors. There's the zeta function, it's a special function, evaluated at 3/2 times the degeneracy factor G. So this is the precise formula when you solve the condition with the full expression for the level density. One physical example, one actual example where Bose-Einstein condensation occurs is liquid helium-4. Helium-4 has spin 0. Therefore, first of all, it's a boson. And secondly, there is no degeneracy. The degeneracy factor is equal to 1. There's no, there are not several spin orientations, but there's no degeneracy. Helium-4 is, of course, composed of 4 nucleons, so its mass is 4 times the atomic mass unit, and this is approximately 6.64 10 to the minus 27 kilograms. And finally, the particle density, a typical particle density of liquid helium-4, you can relate that to the mass density, so you can write that as 1 over the mass of a helium-4 atom times the mass density. Now the mass density, this is typically, a typical value would be 0.14 grams per cubic centimeter. So this translates into a particle density of the order 2.1 times 10 to the 28 particles per cubic meter. And so these are just some experimental values, some empirical values for liquid helium. And you can insert these values into the formula above that we have for the Bose-Einstein temperature. And you find with this formula a Bose-Einstein temperature approximately 3.1 Kelvin. This is not quite the value that you observe experimentally, but it's the correct order of magnitude. The experimental value is 2.17 Kelvin. So it's about 1 Kelvin off. But it's this, as I said, it's the right order of magnitude. It's a few kelvins. Now, the fact that there is a discrepancy is mainly due to the fact that it's not correct to describe liquid helium as a perfect gas. There are interactions between helium atoms, and these interactions become or are non-negligible. So it's not truly a perfect gas, whereas all the calculations that we have done and all the estimates were based on the assumption that we have a perfect gas. Finally, I would like to give just a heuristic argument why Bose-Einstein condensation may have something to do with a phase transition to a superfluid phase. To this end, let us consider the pressure of our Bose gas. The pressure is always 1 over beta and then times the partial derivative of the log of the partition function with respect to volume. But the log of the partition function is simply proportional to volume, and so taking the derivative with respect to volume is tantamount to dividing by volume, so we can simply write the pressure as 1 over beta times the volume times the log of the partition function. Now, let's say we are far below the Bose-Einstein temperature, so we are in the regime where the occupation of the ground state is already macroscopic, already very much larger than 1. In that case, the alpha, which we had already estimated to be minus 1 over the occupation of the ground state, is certainly much smaller than 1. This in turn implies that the log of the grand canonical partition function in our Taylor expansion is dominated by the 0th order term. Because the alpha is very small, so this term proportional to alpha is a small correction, and the log of the grand canonical partition function is dominated by the 0th order term in the Taylor expansion. So, in this limit, the log of the grand canonical partition function is simply proportional to volume times beta to the power minus 3/2, and it's independent of alpha. Inserting this into the formula for the pressure above gives pressure proportional to, well, the volume cancels out, and we divide by beta, so this is proportional to beta to the minus 5/2, or this is proportional to temperature to the power 5/2. And interestingly, the pressure is now independent of alpha and also independent of volume. So it's independent of both alpha and volume, because the volume cancels out. This implies that the partial derivative of the pressure with respect to volume at fixed temperature and fixed particle number is equal to 0. And this implies that the compressibility, strictly speaking the isothermal compressibility, which we had encountered when we discussed stability, thermodynamic stability. It's this kappa index T, which is proportional to the partial derivative of volume with respect to pressure at fixed temperature and particle number. So just the inverse of dP over d volume. Now dP over d volume is 0, and therefore the compressibility, which is the proportional to the inverse of that, diverges. Now this first of all indicates a thermodynamic instability, because in the context of stability we had said that a requirement for, or a prerequisite for a thermodynamic system to be stable is that the compressibility is finite. Here the compressibility diverges, and this is an indication that the system becomes unstable, and this is an indication of a phase transition. Now, in particular, the compressibility, a diverging compressibility, means that the system reacts extremely sensitively to changes in pressure. It's extremely sensitive to changes in pressure. This is a typical signature of the transition to superfluidity. I don't have the time here in this course to go into detail, so I have to stay at the surface here, but I just want to tell you that it's a signature for a phase transition to a superfluid phase that the compressibility has a peak. I mean, it's never truly infinite, but a typical signature is that you have a peak in compressibility, and this is suggested by our result here. We have a diverging, in this idealized treatment, we have a diverging compressibility, and we can view that as a signature of superfluidity.